Hello and welcome back to Oxygen Not Included. In today's episode, we're going to take a deeper look at the rock granulator. The rock granulator, if you recall, was one of the options that I listed for cooling down your base in my big review of all the various cooling technologies. And the reason for that is that the rock granulator has the ability to convert material of one heat capacity to material of a different heat capacity. The most straightforward of these changes is salt to table salt, because you're taking 100 kilograms of salt and converting it to 5 grams of table salt. So effectively what you can do is dump a bunch of heat into the salt and then just delete, more or less, the salt from the game by running it through a rock granulator. 5 grams is virtually nothing compared to 100 kilograms. This is a pretty straightforward and simple process. I'm not going to show it off here today because I think it's a little bit less efficient than the process I'm about to show you, which is using obsidian and sand. Either that or sedimentary rock and sand. They have the same thermal properties, obsidian and sedimentary rock, and both of them convert to sand at a 1-to-1 ratio. And basically the idea here is that obsidian has a specific heat capacity of 0.2, whereas sand has a specific heat capacity of 0.83. And so because you're converting something from a low heat capacity to a high heat capacity, what you want to do is, instead of dumping heat into the obsidian, you want to dump cold, so to speak, into the obsidian. You want to cool that obsidian down, draw all the heat out of it, and then run it through the rock granulator and turn it into a higher heat capacity material, right? Sand here at 0.83, obsidian at 0.2. Basically, for every degree that you cool down the obsidian, right, you're going to get 4 times as much heat capacity out to heat up the resulting sand, right? You could dump for every 4 degrees you dump into obsidian, you get basically 1 degree dumped into sand. That difference in heat capacity is going to be the basis off of which you're able to run a lot of your cooling. Now, I started playing around with various systems to do this, and there were sort of 2 problems. The first problem was that they ended up looking a lot like the ice maker build that I've shown off in a previous video. Namely, you're going to take the material that you want warmed up and run it through a heat exchanger with some other hot material, and you're going to take the material that you want cold and run it through a heat exchanger with some cold material, and that's it. Right? You want to cool down your obsidian, run it on a conveyor loop through a heat exchanger with some sort of cold system, and there you go, right? That's really all there is to it. Then take the sand that's resulting and run it through a heat exchanger with whatever you want to cool down, potentially even the original system that you use to cool down your obsidian, and there you have it, right? There's really not much to it, and it's just, it looked so much like the ice maker system that I've already shown that I felt a lot of viewers wouldn't really get much out of it. If you know how to make the ice maker system, then you probably also know how to make this system. There's not really much more complicated to it. You can still do it off of a single heat exchanger. You can, if that's too complicated, you can use 2 heat exchangers and separate them out. This is the cold one, this is the hot one. But either way, these systems looked very similar. And also, these systems still relied upon more or less reaching the same level of technology, which is that you need to get conveyor rails up. And that kind of has 2 problems with it. One is that conveyor rails are fairly far down in the research tree. I mean, this is 7 specific technologies you need to research before you can research the conveyor rail technology. That's, I don't know, for a lot of people, that's a lot of research to be devoting to something when you're not even really getting a lot of your essential stuff out of it. You're not getting farms, you're not getting any sort of disease management, you're not getting electrolyzers, right? Like, a lot of this stuff is really only going to be used for this one build. That's a lot of research time to devote to things. So that was also kind of one of the reasons why a lot of people didn't want to do it. And more importantly, you need to actually have a duplicate capable of building conveyor rail, right? You need to have a duplicate level up all of their engineering up to mechatronics engineering. That's 5 skill points you need to devote. 5 skill points is something like, I don't know, 60 cycles, somewhere around there. That's a lot of skill points to be devoting to something. And so it really delays when you can get this cooling system online. The earliest you're going to be able to get it online is something like 60 cycles, just because it's going to take you that long to get a single duplicate that can start doing conveyor rail around your base. And you might want to have those sort of original starting duplicates be reserved more towards training to be astronauts, training to be something else. A lot of the skills that you're picking up here, I mean, improved carrying is nice, but improved tinkering and electrical engineering are not really very valuable in a lot of instances. So having a duplicate capable of building conveyor rail is a bit of a headache. And so I wanted to try out a system that was not only different from the conveyor rail system that I've already shown off in my ice maker video, but I also wanted to show off something that didn't require the conveyor rail, that didn't require all the metal that went into building conveyor rail, that didn't require the specific specialized duplicate labor to build the conveyor rail system. And so I began testing out various ideas just using simple storage bins, right? Because rock granulators are a fairly basic technology. You unlock them fairly early on. Here they are on the second tier. You don't even need to do any advanced research. Literally, this could be the second piece of research that you unlock. And because some maps are going to basically put cooling requirements on you that quickly, right? You're going to go into Oasis, or you're going to go into Vulcanea or Iridio, or one of these different like hot asteroids, and you're going to need to start cooling down things really quickly. I wanted to show off something that could be unlocked right away effectively. And so here's what I've come up with. I've done some testing for storage bins, and the conclusion from the testing is that the objects inside storage bins behave exactly the same as objects that are simply dumped on the ground. That it doesn't matter what the storage bin is made out of, doesn't matter if you put any temp shift plates around it or anything like that. They act exactly like materials that have been dumped on the ground. And that kind of simplifies a lot of things, because we can just do the math straight up for how much cooling you can get, or how much heat something can absorb when you just leave it on the ground. What is the heat flux between this salt and this window tile? Well, I know what the thermal conductivity of the window tile is, I know what the thermal conductivity of the salt is, and so I can just calculate exactly how many DTUs per second are going to flow from this heated window tile into this salt, if I know the difference in temperatures between the two. So pretty simple, and this is kind of the point where I said that I don't want to use salt, because salt has a thermal conductivity of 0.444, whereas both sand and obsidian have a thermal conductivity of 2. That's more than 4 times the thermal conductivity, because thermal conductivity is going to be one of the rate limiting steps of how much heat we can draw from the system. I decided to go with the obsidian as well. And this is what an example build might look like. Effectively, what we're doing here is that we have a heated pad. In this case, I've made it out of diamond. You can make it out of a less conductive material. That's fine. It will be a little bit less efficient, right? Because again, this thermal flux is what is critical to what the capacity of the system is. But here I've designed it almost for overkill. I've got all these storage bins here, and I've only got 4 thermo-regulators down here. And roughly speaking, if you have a 280-degree difference between obsidian or sedimentary rock sitting in a storage bin and the window tile, diamond window tile underneath it, 280 degrees of temperature difference is enough to cool down an entire thermo-regulator. Just one storage bin, if the difference is high enough, can get you all of that cooling. Right? That is the heat flux through this system. 280 degree difference between obsidian and diamond is enough to cool down a thermoregulator. In this instance, I've put 4 storage bins per thermoregulator. That way, I only need to maintain a 70 degree difference between the contents of these storage bins and the temperature of this window tile. If I used a less conductive tile here, if I used some sort of metal tile, like I made it out of gold, right? This has a thermal conductivity of 60. It's going to be 3/4 of that of the window tile. Roughly speaking, you're going to get 3/4 as much heat flux through that system. Something to keep in mind. It's not a huge change, right? The extra efficiency is nice, but because I am going 4 storage bins per window tile, I'm able to get away with this. This only requires right now a 70 degree difference between the contents of the storage bin and the window tile that I have down here. So how would we kind of design the system? Well, we'd want to have a cooling pad area where we are going to put a bunch of our obsidian. Right here, we're going to take a bunch of obsidian and we're going to cool it down. And I'm going to take 1/4 of the thermoregulators that I put in this system and use them to cool down that system. So here I have a ventilation loop where basically one thermoregulator is keeping this window tile cool, right? and the other 3 are off cooling some separate system, some separate hypothetical system. Maybe they're taking your oxygen and cooling it down, right? You can imagine a loop like that, where you're taking the output from some sort of electrolyzer and running it through 3 thermo-regulators, right, to get it down by 42 degrees. So your oxygen, instead of coming out at, say, 70 degrees, would come out at 28 degrees, right? You could do something like that. But yeah, I have my obsidian on this cooling pad right here, and I have my sand resulting from this rock granulator sitting right here and cooling this area down. Now, it's fairly easy to maintain a 70-degree difference because, again, this window tile presumably is going to be at a temperature around negative 200 degrees, right? I'm just going to be running hydrogen through the system, cooling down this window tile. And it's going to be going straight into the obsidian that I have right here, which is a fairly low specific heat capacity. And the sand is a fairly large specific heat capacity, right? So that's why I only need to use 1/4 of these thermo-regulators to keep this thing cool. If I get this obsidian cooled down to, say, 100 degrees before I turn it into sand and run it down here, I mean, this system could be as low as negative 30 degrees and still provide enough cooling for these thermo-regulators, right? So if you're cooling down your obsidian through these storage bins to a negative 100-degree value, it's going to be very simple. You wouldn't even need steel components for these thermo-regulators to make this work. So I think 70 degrees is very doable. I think in actuality, right, if you really got the system tuned and efficient, you could have basically this entire thing be thermo-regulators down here. Instead of putting 4 down here, you could put 8 down here, and it would work just fine. Right, with 2 of those thermo-regulators supplying the cooling to this loop right here. Because then I think 140-degree difference is very doable. And even if we were using gold metal tile as opposed to diamond metal tile, I mean, we're still only talking about a 200-degree difference. If I get this stuff down to, you know, negative 100, this tile could be 100 degrees and it would still be just fine. An important thing to note, though, is that I want to keep this entire room vacuumed, though. So what I would do is I would have some sort of liquid lock, right? We can say fill water, something like this, right? I would have a liquid lock separating this area. I would probably have an atmosuit dock if I had access to atmosuits. I'd have an atmosuit dock right here so that they would go through here. They wouldn't gain any stress from going through the water. They'd be able to breathe as they're operating the rock granulator. But the other thing I would do is, besides keeping this vacuum, that way I don't have heat transfer from my cold pad to my heat pad, I would also just limit the amount of storage that I'm keeping in each of these bins. This will make sure that these things cool down as quickly as possible, right? Each one of these storage bins basically holds 1 batch for this rock granulator. And so I'm able to just kind of process things very quickly because I don't have a huge thermal mass in the storage bin that's just being very, very slowly cooled down. I have a very small thermal mass. It's going to cool down very quickly and then get converted to sand. And then once I'm done with that sand, I can replace it. So basically, the system is going to require some amount of labor on your part in that it isn't automated. It's basically you need to queue up things in the rock granulator. You need to make sure that these storage bins are being replenished with fresh obsidian or sedimentary rock. And then you need to, once all of these fill up with sand, occasionally go through and tell them to all empty, right? And then sweep up that and put it to a higher priority storage bin. So I'd basically have I'd have a storage bin, I don't know, I mean, somewhere over here, let's say. And I would say, okay, this storage bin is going to have a priority of like 6, and all these storage bins are going to have a priority of 5, but I'm going to set this one to be sweep only, right? So I'd set a storage bin to be sweep only, but at a higher priority. And then periodically, once these things filled up with hot sand, I would go ahead and say, okay, empty out all your contents. You're not allowed to have sand anymore. All the sand drops on the ground. I designate all that sand to be swept up. And then the duplicates will all bring it to the higher priority storage bin. So it's going to require a sort of periodic emptying like that. If you don't really want to get the maximum possible efficiency out of the system, that's perfectly fine. You can just go through and say, look, just hold as much as you like, all right? Like, you probably want to keep it around 100 at the start, just so that all of these get something filled in them. And then you kind of want to just go ahead and say, okay, let's turn it all to 1,000 kilograms, and then copy settings and go across here and just kind of slowly fill all these things up. Because again, if you had all of your sand in one of these storage bins, it's going to transfer heat 1/16 as quickly as if you had it distributed across all of these storage bins, right? The surface area does matter for this process. But this is sort of the general makeup of what this system would look like. And I have tested it. At least I've tested the basic principles of this thing. I'm going to kind of refine this build a little bit more and maybe showcase like a specific build for this thing. But this is generally what your system would look like, is sort of the point of this video. And it is effective enough that basically just a single one of these storage bins, if the temperature difference between its contents and this window tile are high enough, a single one of these storage bins could keep an entire thermoregulator cool, right? This is a completely possible thing, completely doable thing within the temperature ranges that we're talking about, within the temperature ranges that are available, particularly if you have steel components. This is very doable. And even if you don't have steel components, again, so long as this is sufficiently cold, you're going to be fine, right? You're going to be able to keep this system at a very low temperature so long as you keep the obsidian that's coming in at a sufficiently low temperature. Booting up this system from sort of cold is going to be a little bit more difficult because you're not going to have any of this cooling sort of done for you, right? In the beginning, you're going to need to put a lot of energy into cooling down this cooling pad, and that's going to create a lot of heat in this room over here. So you probably, before you do anything, maybe just want to have a lot of sand or some sort of thermal mass in these storage bins. Something that you're not going to care about. A good idea might be to just fill it with salt, right? And kind of get some passive cooling that way, because you can delete the salt really easily. And then later, after you've gotten this pad nice and cool by dumping a bunch of heat into the salt and running it through the rock granulator, then you can say, okay, I don't want salt in here anymore. I want sand in here. Replace that with sand, and then you're off to the races with a more efficient system. The advantage of having things where I have 4 storage bins to 1 thermoregulator in that system then is that I can get, even though the sand has roughly 1/4 of the thermal conductivity as of the obsidian or the sand, right? Even though the salt is not as good a conductor, because I have 4 storage bins for it, it's still going to probably be enough to maintain this thermoregulator at a decent temperature. Now, let's talk a little bit about your thermoregulator sort of maintenance system. This is going to be something that's pretty basic for a lot of people who've kind of advanced through the game and played a lot of the stuff, but it's worth going over right here. So I have an automation system here, and this automation system is basically an AND gate attached to each of these thermoregulators. The AND gate is looking to make sure that 2 properties are true. It wants to make sure that the coolant that's running through this thermoregulator, in this case it would be hydrogen, it wants to make sure that coolant isn't so cold that if I were to run it through the thermoregulator, I would break my pipes because the material would condense, right? So I don't want the resulting temperature of the hydrogen to go below -252 degrees because it would liquefy the hydrogen and break my pipes. So that's one condition that has to be met for this thing to run. And the other condition that I want to have set before this can run is I don't want the temperature, the ambient temperature around the thermoregulator to be so high that it melts or breaks the thermoregulator, right? I don't want to take overheat damage on my thermoregulator. And so I have a temperature sensor in here and basically saying that the temperature has to be below 250 degrees. So if both these conditions are true, if the coolant that's coming in is sufficiently warm that I can still cool it down, and if the ambient temperature around the thermoregulator is sufficiently low that I won't break it by adding more heat, then the system will run. And the way that I've set up the ventilation basically is that the input is coming in through this line, and it reaches the thermoregulator and says, if the thermoregulator is on, then I will continue on through the thermoregulator, in which case it comes out the outlet port of the thermoregulator and then it continues on its way. And if it says the thermoregulator is off because one of those 2 conditions is not met, either the coolant is too cold or the room is too hot, then it goes into a bridge and bridges over and then continues on its way, right? So if the thermoregulator is not on, this line will bypass the thermoregulator and just continue on its loop, right? So for example, if the condition that isn't met is that the coolant is too cold, well, great. The coolant will just continue on its way and then heat exchange with this system over here, hopefully become warmer in the process, come back, and then it will be warm enough for the system to turn on. If the condition is that the room itself is too hot, great. Just have the coolant kind of be in standby while more heat transfer occurs through this window tile, right? So this prevents the system from breaking. I have similar things set up over here, right? Exact same idea. I have my input line. It reaches the thermo-regulator. If the thermo-regulator is on, then it goes to the thermo-regulator and then goes out. And if not, it takes a bridge through and bypasses the system. Easy peasy. This is kind of all old hat. I am replacing the typical hydrogen gas in the system with ethanol gas. Ethanol gas has a lower specific heat capacity than hydrogen, 2.148 versus the 2.4 of hydrogen, but has a much higher thermal conductivity. And thermal conductivity is really what we're going to care about in this system, right? Because we want to make sure, we want to get as high a temperature difference as possible between this window tile and this storage bin, which means we want to have as low a temperature difference as possible between this window tile and this thermo-regulator, because the higher the temperature difference, then the lower this window tile needs to be in terms of temperature to prevent this thermo-regulator from melting, right? So we want a really highly conductive material in this room. The most highly conductive material gas that we can come up with at this point that's sort of reasonable is ethanol. This ethanol still works fine if the system goes cold because I've only got like 2 grams of it in the air, right? So, or 2 kilograms of it in the air. So if it condenses, it'll just be a liquid that's still cooling these thermoregulators and not be enough to flood the thermoregulators. So ethanol gas at the current moment is a really efficient cooling gas, really great thermal properties, works perfectly in the system. So I'd use that if you have it available. If not, hydrogen works perfectly fine. Again, the system will probably be a little bit less efficient with hydrogen, but it'll still work, right? We've built the system so conservatively that it should function regardless. So that's kind of it for the system. I think I've explained pretty much all the parts of it, sort of what the thermal properties are of things in storage bins, how they interact with things thermally, and the basic build would basically be an insulated room, or at least this part needs to be insulated, and you don't, I guess this cooling pad and this heating pad need to be insulated. All this stuff right here, right, all this could be normal tile simply because this is a vacuumed out room, so it's going to provide perfect insulation anyways. But vacuumed out room, long rows of storage bins. When booting up the system, you fill these storage bins with salt. You let this thing heat up and in the process cool down this cooling pad over here. You stack a bunch of obsidian in these storage bins. Once your salt's kind of gotten sufficiently hot that it's not really cooling down the system anymore, you run it through your rock granulator and turn it into table salt. The table salt goes off somewhere else. It's only 5 grams of something really hot, so it doesn't really matter. And then you start filling these storage bins up with sand, and that's going to be your permanent cooling from then on. Periodically, you're going to need to go through and either increase the capacity of these storage bins, right, from like 100 kilograms to 1,000, 1,000 to 10,000, so on and so forth, to keep the cooling going. And eventually, every once in a while, you're just going to need to empty these things out completely and cart them off somewhere else, right? Because eventually, this sand is going to heat up, right? But this system allows you to basically take 3 thermoregulators and run them to go cool some system, like the oxygen that's coming out of some sort of electrolyzer room, right? And take one of those 4, 1 out of 4, and use it to cool down your cooling pad. And this is going to be how you net your cooling, right? This is going to be a closed loop that'll just cool itself, and this is going to be your sort of open-ended part that goes and cools down whatever else you want to cool down. Pretty simple system. I'm hoping to kind of refine this and test it out and play around with it and then show you guys off something that's kind of finished, right? I don't have any gas running through the system or anything like that, but in principle, this system should work pretty much exactly as advertised. I've tested out all the relevant questionable things, and I think is a very viable means of cooling down your base in the very early game. There isn't a whole lot of moving parts here. You do need access to thermoregulators or some sort of thing like that, because you do ultimately need to cool down your obsidian somehow. But other than that, I mean, this is pretty simple, pretty straightforward, and doesn't require any specialty dupes, doesn't require anything like that. No masses of metal being invested in some large conveyor rail heat exchanger. If you guys really want some sort of heat exchanger system using conveyor rail, that's pretty easy to set up as well. But I do urge you to go and look at my ice maker video, because that video I think just kind of showcases everything that needs to be showcased about how you make a heat exchanger with a conveyor rail system. But yeah, that's it for this episode, I think, and I'll catch you guys next time.